Hello everyone. Okay, now it's the last video for lecture 9, and then I think 10 we will cover in the next chapter. Sorry, not the next chapter. The next part of the gases we will cover in lecture 10. So here we're just going to wrap up our discussion about the gas laws and the ideal gas law. Okay. All right. So we talked about Avogadro's law, where the number of molecules are proportional to the volume of gas that a gas occupies. Okay. So for example, think about the reaction between HCl and ammonia, which combine in a 1-to-1 ratio by volume. So this is because of the balance of chemical equation. So the balanced chemical equation, as we see below. So this is because of the balanced chemical reaction that's below, where one molecule of HCl is consumed for every molecule of ammonia. So this means that equal volumes of gases contain the same number of molecules. And we can see this below right here. So we can also interpret this reaction as one volume of ammonia plus one volume of hydrogen chloride gives us one volume of hydrogen chloride gives us ammonium chloride salt, where the volume can be any unit, milliliters, liters, but those are probably the two most common ones we'll encounter, milliliters and liters. Okay, so now let's talk about the ideal gas equation. So if we combine all these gas laws we talk about, it comes together in this one kind of all-including reaction called the ideal gas law, which is right here, PV equals nRT. And so we've known about pressure, volume, N is for moles, and then R is the gas proportionality constant, known as the ideal gas constant, and T is the absolute temperature in Kelvin. So most chemists use the following set of units by convention. Pressure is atmosphere, T is kelvins, volume is liters, and N is moles. So we can actually calculate the R value by using any set of variables that we collect in an experiment. So let's say for exactly 1 mole of gas at 1.000 atmospheres and 0 degrees Celsius, this is what we call standard temperature and pressure conditions. So we refer to these conditions so scientists all over the world could report their results for gases, and when they study gases in a standard that is kind of uniform or not universal to everyone. So we're not reporting units in different standard conditions, so we don't get different results. So it's kind of to piece together that results are more interpretable across the scientific community. So if we do the standard conditions, 1 mole, 1 atm, and 0 degrees Celsius, the volume we find is approximately 24.4, or more accurately, 22.414 liters. So we plug in these values here, we get the value for the gas constant, 0.082057 liters, atmospheres, moles, Kelvin. Okay. So you might think, so we can just plug in any number and it should give us 0.082057. No, that's not how it works. What you have to do is measure these individually in experiment. So you maybe tweak one variable, then record the variables for the others. Say I have 5 liters of gas. What's the pressure at, say, 25 degrees Celsius, and how many moles is that amount of gas equal to? So you would do something like that in an experiment and find the value for R. Okay, so that's the gas constant. So this constant will be given. You do not need to memorize any of this. I'll give you the gas constant always, but this is the only one I will provide. So you can actually use a different gas constant, which have different units. For example, millimeters of mercury, torr, different pressure units. However, probably the only one I will provide on the kind of formula sheet is this one right here. Okay. So for these calculations, we can simplify this to just 4 sig figs. So usually it's 0.08206, or you can also use 0.0821 liters atmospheres. But usually I would use all 4 sig figs for in this case. Okay. So we can actually use this equation now to predict any value if we know the other 3, because we know R because it's a constant, right? So we can predict any other value given we know R and 3 of the other variables. So we can predict any unknown variable given the initial conditions. So we don't have to keep anything constant. So that's kind of more like what that's kind of how we do a chemical reaction, right? We're not exactly keeping volume constant, and we're not exactly keeping pressure. Sometimes we don't keep pressure constant, and oftentimes we don't keep temperature constant because there's a change in temperature. So this equation is very handy for chemists who do reactions, who study reactions. Okay, so now we talk about these gas laws, right? That's kind of hard to remember. So let's try to put this into solving some problems. Okay. So the first exercise we'll do is many gases are available for use in the lab in compressed gas cylinders. So if you ever worked in a lab or worked in a hospital, you may see cylinders like oxygen and compressed gas cylinders, because that's the most convenient way to get gases from a container. Okay. And they're stored at high pressures because to really keep all that gas in there, you need to store it under a very strong cylinder, and it's at high pressure. So let's calculate the mass of oxygen that can be stored. In at 21 degrees Celsius and 170 atmospheres in a cylinder with a volume of 6 liters. Sorry, not 6 liters. That should be 60. I forgot to change that. See, always miss something. Okay, 60 liters. All right. So let's. We pretty much have everything we might need in the ideal gas law. So when we need to calculate the mass of something, usually we have to go through the ideal gas law because of moles. But we also have pressure and temperature in our variables here, so we can't use any of the individual gas laws. So we have to use the ideal gas law. So PV equals nRT. Okay. So if we list all our values here, it's kind of listed for us. So this is our volume. This is our pressure. Oops, not R. Our pressure, and here's our temperature conveniently converted for us into kelvins. So we can use that now for our equation here. So PV equals nRT. Let's plug in the values. So first, let's rearrange the equation. We want to solve for N because we know from N equals mass. So moles of oxygen equals mass of oxygen over molar mass of oxygen. So from there, we can solve for the mass of oxygen if we know NO2 times the molar mass of oxygen. So we need to figure out, we need this variable first, right? We need to figure that out first to determine how much mass of oxygen is in the tank. Okay, so we're going to solve for N. So we do PV equals nRT, divide both sides by RT, and now we have a situation where N equals PV over RT, and we can solve for N. So N in this case would be 60 liters times the pressure. Oops, I put them backwards, but that's all right. 170 atm divided by the ideal gas constant, 0.08206. So if you don't want to write all the units, you don't have to, but I will just to show how that units cancel. Liters times ATM. And then we have mole Kelvin. Okay. And then the temperature is 294 K. Like that. All right. So we can everything will cancel. Liters cancel. Atmospheres cancel. Kelvin cancel. And since moles is in the bottom of is in the bottom of the denominator of the gas constant, it's going to appear on the top of our as mole. So we're going to end up with mole. Okay, so in this case, we're going to end up with mole as we calculate this. And if we calculate this, we get 423 mole Kelvin. Or, you know, if we want to avoid a calculation error, we can actually do this instead. Okay, so we could do this. But actually, it might be more confusing if we do it that way. So let's do it sequentially. I think it's fine. Sorry about that. So N. So this will give us around 423 moles of oxygen. All right. So now if we go to the bottom here, we take our 423 moles of oxygen. We now have our number of moles here. In our mass equation here, so we know that we have to multiply this by the molar mass times 1 mole. Sorry, we want to get rid of moles, so we're going to put mole oxygen on the bottom here, and on the top will be 32.00 grams of oxygen. Okay, and that will give us 1.35 times 10 to the fourth grams of oxygen. Okay, so in this case, we are going to consider I believe we would consider 3 sig figs in this case, but let me just double check here that we are using 3 sig figs in our value, so we're not mistaken here. I believe 3 sig figs should be right, but it might be actually a little bit incorrect. Okay. Okay. All right, so we want to use 3 sig figs. I think it's because so if we think about it in terms of this, when we in our Kelvin value, so just imagine it's around 170. So we put that dot there, right? So everything has 3 sig figs, liters, pressure, and then for the temperature, we're looking at the Kelvin value. So we count how many sig figs are there before the decimal, because that's how we would consider the sig figs in terms of the conversion from Celsius to Kelvin. So it should be 3, no decimal places, so 294. So that's 3 sig figs, right? So when we divide, that'll be 3 sig figs. So 1.35 grams of oxygen, or we could say 13.5 kilograms oxygen. So that's a lot of oxygen, right? Okay, so let's try another example. So the key to doing these problems is not just, I want to not just plugging in the numbers, but thinking about like what all these values mean. So if we look at this equation, it states that pressure and volume are inversely proportional, and then it's directly proportional to the number of moles in temperature. Okay, so but we can understand these problems by doing more examples. So let's do that. Okay, so let's try this example. All right, so we have calculate the mass of the air in a hot air balloon that has a volume of 4.00 times 10 to the 5th liters when the temperature of the gas is 30 degrees Celsius. All right, and the pressure is 748 millimeters of mercury. So let's assume that the air in the atmosphere is a mixture of roughly 78% nitrogen, 20% oxygen, 21% oxygen, and 1% argon. Okay? And in this case, the molecular mass or weight or average molecular weight of the air is about 29.0 grams per mole. And that's due to the arithmetic mean of all those gases I just mentioned. Okay? So we need to calculate mass of air. To do that, we need to find the moles of gas. And once we have the moles of gas, we can use the molar mass again to figure out the mass of air. Okay? So PV equals nRT. We see here we have our volume, our pressure, converted to us in the proper units already. So we don't need to do that necessarily, but if that picture wasn't there, we would be expected to calculate that pressure. Okay? And then here's the temperature in Kelvin. So let's just do that very quickly. So here the volume equals 4.00 times 10 to the 5th liters. All right. Our pressure, so pressure equals 748 millimeters of mercury, but we need to convert that to atmospheres, and we know 1 atmosphere equals 760 millimeters of mercury, and that would equal to 0.984 atmospheres. Okay? And then we have temperature here. Temperature equals 30.2 plus 273 Kelvin, and that would equal to 303 Kelvin. Okay, so you could use 273, just 273, or 273.15. I do not care. It does not matter to me. Okay. Now let's plug in our equation again. We're solving for moles again. So N equals PV over RT. Okay, so in this case we have 0.984 atmospheres. The volume is going to be 4.00 times 10 to the 5th liters. And then we get our gas constant here, 0.08206 with all its units. And then we have our temperature here, 303 K. Okay, so all the units will cancel. And what we're left with is moles. And so we get 1.58 times 10 to the 4th moles of air. So you see here, so we get a large amount of air, and we had a very large volume, so it kind of dictates that volume is proportional to the amount of particles that it occupies. Okay, so they're directly related. All right, so that's the moles of air, and we see our values here are around 3 sig figs, so that makes sense. So now let's convert the air now to mass. So we take our moles of air, 1.58 times 10 to the 4th. And we know that for 1 mole of air, it's equal to 29.0 grams per mole. So in the question, you have to be able to kind of identify that the molar masses there are just given there for each element. But we're talking about air, right? And the average of that is 29.0 grams. So you might want to highlight this value when doing this problem to say, okay, I'm going to use this molar mass, not the other ones, because this one is for the air mixture and not pure gas, or pure like elemental gas. Okay. All right. So if we do that, we get, so let's put it right here underneath. We will get a value of 4.58 times 10 to the 5th grams of air. Okay, so that's how we solve this one. We're solving for mass, but sometimes we may solve for pressure, temperature. It doesn't matter, because as long as we have this equation, we just need to rearrange the equation and then solve for the unknown variable. Okay, so 4.58 times 10 to the 5th grams of air. So that's a lot of air. Okay, so let's end this lecture here, and we'll pick up lecture 10 with the rest of these slides, and then I'll move on to kinetic molecular theory of gases, and we'll talk about why the ideal gas law doesn't necessarily work for actual gases. So kind of a conundrum there. So I'll see everyone in the next video. All right, take care.